Welcome to Hot Chips 34. Session 6, ADAS and Grace.
All right. Hello, everyone. Welcome to the next session at Hot Chips. I'm Ian Brott from ARM, and we've got three excellent talks teed up for you today. The first talk, titled NVIDIA's Orin System on Chip, will be presented by Michael Ditty from NVIDIA. Michael's a senior director at NVIDIA working on the system architecture team. During his 17 years at NVIDIA, he's worked on projects ranging from the first H.264 decoder to the K1 to chips for Nintendo Switch. And most recently, he's been serving as chief architect for Orin.
Hi, my name is Mike Ditty. I am one of the system architects at NVIDIA. I was the lead architect for our Orin system on a chip, and I'm here today to talk about that. So yeah, we had previously had the Xavier SoC, and Orin is our follow-on, focused on automotive and embedded markets. And as we looked at Xavier and where can we improve, there were some key areas we wanted to invest in, right? We wanted to improve the CPU performance. We did that going by a 12-core ARM Cortex A78 AE, so with automotive enhancements. We looked at the next generation GPU we had available, and so Orin includes our Ampere GPU. We increased the overall SM units in it, took all the Ampere features, giving us 5.3 FP32 CUDA teraflops, 10.6 FP16 CUDA teraflops. So a big bump over what was available in Xavier. We looked at bandwidth critical to the chip, and bumped up to LPDDR5, giving us 205 gigabytes per second. For process, we went with Samsung 8 nanometer, giving us improvements over Xavier. One of the big areas that we hadn't done previously is looking at safety island. So we added a safety island, giving us 10K DMIPS of ASIL D compute. This is made up of 4 lockstep core ARM Cortex R52 CPUs. And then we get over to the I/O. One of the enhancements we made for Orin was enabling 4x 10 gigabit Ethernet. So previously, we had 1 gigabit Ethernet, but 4 10 gigabit Ethernet enabled some new capabilities in the chip. We continue to have 24 SerDes lanes. Those are used for things like USB, PCIe, and Ethernet, and then we also continue to have 16 CSI camera lanes. A big level area of improvement was on the DL side. So on deep learning, we bumped up the performance to 275 int8 DL tops. 170 of those are coming from the GPU side. 105 of those come from 2 DLA instances that we have. DLA is our deep learning accelerator that we took from Xavier and improved. And then we have 85 FP16 DL tops, and those are coming from just the GPU. On Xavier, we rolled out a programmable vision accelerator, and so we continued to enhance the capabilities there. And then in terms of overall safety, similar to Xavier, we continued giving an overall ASIL B chip with ASIL D systematics, enabling customers to build complete solutions meeting the safety requirements for automotive. So let's dive into some specifics there. Starting with the CPU, we work closely with ARM on automotive enhancements to their ARM cores. And so there's a variety of enhancements, including diagnostics, and one of the key features is the ability to run the CPUs in lockstep mode. So we have 3 CPU clusters. Each of those are made up of 4 cores each. Within that, you can switch that to lock mode and run 2 cores in each cluster, and the other 2 are shadowing it with a few cycle delay and giving full coverage of the execution on those pipelines. So we have that mode we can run in. We can optionally do that per cluster, or depending on the customer's usage and the diagnostic desires, you can run it all in non-lockstep mode also. And so that was a big investment. That the AE core from ARM for the A78 version for automotive also does include pointer authentication features and a couple other enhancements that weren't in the original A78. For frequency, the CPU, depending on product, runs at up to 2.2 gigahertz frequency. For caching, we have 64 kilobyte L1 iCache and 64 kilobyte Dcache. We have 256 kilobytes of the L2, which is per core. And then we have a 2 megabyte L3 per cluster. And then kind of at a system level, we have a 4 megabyte cache. So that kind of makes up our overall CPU cluster. In terms of performance, we have, these are the estimated spec scores here. So we have spec 2K6 for a single core, 31.8. Spec 2K6 rate, 269.5. We have the floating point single core at 41.6. And again, the rate for 12 cores at 332. Spec 2K17, integer single core is at 4.04, and then the rate 12 core 39.36. And then I included the Geekbench numbers here. So single core Geekbench 754, 12 core Geekbench 7,773. So all of these numbers are run on our Jetson boards. CPU is set at 2.2 gigahertz. Memory is set to 3.2 for these tests. And again, depending on platform, some of these will vary both frequencies available and different OS platforms. So moving on from there, the safety island. So I mentioned this earlier. As we looked at the needs in automotive, one of the things we found was a continued desire for more and more ASIL-D compute. And a sharing of data with the at higher speeds than we might do with an external MCU. So if you look at Xavier, a lot of ASIL-D compute is provided by external MCU. We saw a need to augment that with additional capabilities on the chip. So we looked at building an isolated island on the chip, achieving ASIL-D diagnostic metrics for all the components within it. And so this is made up of 4 R52 CPU pairs. So it's a total of 8 cores, but only 4 logical. And then the core pairs each share a cache, tightly coupled memory, and we have dedicated memory for each of the core pairs. We have an overall shared memory that they can all use, and also that we can use for the other components within the island as needed. So a fair amount of memory for on chip. We have a security engine here. Security engine does have some processing capabilities within it. That is, again, going to be lockstep. So we get high diagnostic coverage. We have crypto accelerators in that. We have a DMA for kind of moving data in and out from the SoC to these SRAMs or from various IOs. And then we have a variety of IO capabilities. So a hardware safety manager is communicating with kind of the rest of the SoC to signal errors. We have SPI here, 2 CAN controllers. We have a number of UARTs, GPIOs, and then we have some kind of standard hardware synchronization primitives, timers, the usual things you would put with a core like this. This does have access to the rest of the SoC, both memory and kind of configuration register access. And so there's a variety of enhancements built into that interface to improve the isolation between the two. So even though we're sending out requests to that side, we need to protect those well, allow the outside not to have impact to be able to hang the safety island. So there's a variety of capabilities to limit or protect communication going to the outside world there. So in terms of specifics, I mentioned 4 Cortex R52 lockstep pairs. So again, it's eight physical cores, each of them paired up, and usable only is 4. We have 10 10K DMIPs, 32 kilobyte iCache and Dcache per core pair. We have a 512 kilobyte tightly coupled memory. That is spread across a couple instances of memory based on the ports available in the R52. And then we have a 3 megabyte shared SRAM that's kind of partitioned across all of those and available. So a total of 5 megabytes of memory along with the cores in this. And so this is enabling us to move some things on chip, to share data easily with the rest of the SoC and the A-class cores, and is a key addition to Orin. Next up, we have the Ampere GPU. The features here are really based on the Ampere architecture. We doubled up from Xavier, so we have 2 GPCs, a total of 8 TPCs, 16 SMs. The cache was bumped up, 192 kilobyte L1 cache. One of the other places we improved was we bumped to a 4 megabyte L2 cache with the DL performance increases in the Ampere architecture, and the DRAM bandwidth, only scaling so far. The caching subsystem was critical, so we bumped this up to 4 meg from the Xavier levels. And then we have the enhanced tensor core similar to in GA100, and so this doubled up the int8 performance over what we had previously in Xavier, and then by putting down twice as much, we have 4x the overall kind of throughput capability on DL. Along with the Ampere GPU, there's a number of compute enhancements that have been talked about publicly already with Ampere. Our GPU can support MIG. We have 2 MIG instances. Right now, that's not planned to be supported in software, but the Ampere GPU is capable of that in Orin. We have a sparsity, and so that's our same sparsity capabilities as an Ampere for deep learning throughput increase. And then doubled up the CUDA floating point performance, also similar to what's in Ampere. So moving on from DL, or moving on to the next part of deep learning, right? We built the next gen DLA. So DLA is our deep learning accelerator. I believe at Hot Chips a few years back, we went in depth into the DLA architecture for Xavier. And so we had a big performance increase here to 52 and a half tops of int8 perf. Now you'll notice, you may have noticed earlier, FP16 used to be available in DLA. As we looked at how to spend area, how to build a power efficient design, right? The point of DLA is to take those networks that fit well on DLA, that are understood well, and run them very efficiently power wise. So it's purposely not as programmable as the GPU. It's purposely more limited to a specific subset of, we think, the most valuable capabilities, because that improves our performance per watt, right? Not adding a ton of capabilities and a programmable microprocessor or vector pipes gives us better perf per watt. So there's a trade-off we look at. And one of the things we decided as we looked at Orin was focusing DLA on int8, removing the overhead of floating point from the hardware and improving the int8 perf per watt, and also the area, so making it easier to fit 2 of them in. So that's one of the big changes, was just how do we efficiently use the area and power, and you'll see that in later also. One of the key things we did was the DLA. We made sure that the math pipeline was compatible with the GPU. There had been some cases on Xavier where it just required slightly different tweaks within the network or training to use the same DL network on DLA versus GPU. And so we made sure that accumulators and those things look exactly the same. And so it's easier to port, right? It's easier for our TensorRT to handle. We also have a structured sparsity in the design. And then it's programmed through TensorRT API, which is the same as you use to do inference on the GPU. So in terms of performance, some key enhancements. One, we added kind of a number of convolution pipes, as you can see in the picture, allowing us to kind of scale up performance as we add more. We added structured sparsity. One of the things people might have noticed or you might wonder about is we bumped up the memory size here. On Xavier, we had a shared SRAM available between Programmable Vision Accelerator and DLA. As we looked at area, we looked at the wiring cost to get high bandwidth to that memory. And as we were going to add units or shift things around, that large SRAM and the wiring for it was fairly expensive. The wiring actually, in some cases, became a significant portion of the area, depending on the bandwidth we required. And so what we found is we were better off dedicating some memory to the DLAs and the PVAs and giving them more larger SRAMs internally. And overall, we didn't increase area by doing that, and we were able to give dedicated buffering to each of the units. So that was a trade-off that, as we continue to shrink process, I think we see more of, where the wire cost is high, memories are a bit cheaper relative to the routing. So that was a significant change, and we no longer have that shared SRAM that we had previously. We added hardware support for layer scheduling. So if you look at where some of the overheads are on Xavier DLA, layer scheduling becomes a significant portion of what's running on that microcontroller. So we moved more scheduling capabilities into hardware. We added depthwise convolution support into the design. And then we kind of looked at what kind of fixed functions post-processing were missing. So we added softmax, clamped ReLU, exclusive average polling, per channel scaling, full channel normalization, kind of some key features that were missing from the previous DLA, so that we could do more within the DLA pipeline itself. So I talked earlier about adding multiple Ethernet ports. We support and we've publicly talked about various automotive customers doing multi-Orin designs, right? And one of the key things to enable when you're doing multi-Orin designs is, how do I share data efficiently between those, right? When we do 4 Orin designs or 2 or 4 designs today, those are not, those are multi-node, they're multi-OS, there's not coherency between them, but we do want to share data. And so we support up to 4 Orin SoCs with direct high-speed connections. So you have 2 options for that connection. You can do Gen 4 PCIe by 4. So we have 3 by 4 lanes you can use to talk to the other Orins. And so what we do for that PCIe is we support both root port and endpoint modes. So we can connect directly the 2 SoCs together, no switches required, no sharing of those interfaces with other devices. And that can be very high-speed communication. We also support 10 gigabit Ethernet now, right? We have 4 lanes, so 3 of them can be used to enable high-speed Ethernet between these Orin chips. And why would you use that versus PCIe? So in some cases, these multiple Orins you want to spread across the car, right? You may have various different usages for them, but want to have some high-speed data between them. Ethernet is easier to run longer distances, so versus PCIe. So we have both capabilities. Different platforms and customers are doing both, and we try and abstract kind of that interface away in software where possible. So that's what those multi-core Orins look like, and and some of the usage of both 10 gig and our many PCIe lanes that we have. So some additional enhancements in the SoC. There's a lot there. I didn't talk about all. I don't give specs for every piece, but I wanted to highlight some key changes or enhancements or capabilities. One is we do support AV1, both video encode and decode. So that's in hardware, full support for encoding and decoding AV1. We have AK video output, and so not generally used in vehicles, but in the embedded space, we have the capability to drive AK output. I mentioned 10 gig Ethernet. We did improve and continue to improve our optical flow accelerator. So we talked some in the past about, we have this engine that's analyzing the differences between images and looking for data movement or pixel movement in objects within. And so we did a big overhaul of optical flow to improve its accuracy and capabilities. We continue to improve the ISP to improve image quality, efficiency, perf and power. And then we as I mentioned, we continue to have Gen 4 PCIe in the design. So overall, a big set of enhancements, many more things around security and other improvements in the chip. But these were some of the key things I wanted to additionally highlight. So what does that give us in terms of performance, right? So if we look at raw specs, right, Int8 tops, we have 8x the DL performance, going from 32 up to 275. We have 3.7x in CUDA tops. I mentioned we kind of doubled up the per clock performance. We also doubled up the engines. The frequency is reflected a bit in the 3.7. So 1.4 to 5.3 CUDA FP16 flops. DLA itself was a 9x increase. Right, we had 11.4 previously, and now we're bumped up to 105. On the CPU side, 1.9x CPU increase. So we went from 140 spec-int 2K6 estimated to 269. And so, and again, that's on our high-end Orin with 12 cores. Different platforms will have different number of those, but we're pushing for as close to 2x CPU as we could get in terms of both single thread perf is providing some of that, and then the additional 4 cores. And then 50% increase in DRAM bandwidth up to 205 gigabytes per second. Okay, and now looking at our ML perf performance. Here we have this is ML perf. We're comparing Xavier's 1.1 submission of ML perf versus the latest Orin 2.0 submission. And as you look across this, you'll see that we kind of range in performance bump from 2 to 5x. And so ResNet 50 is kind of 3x performance. SSD small, kind of 2x, SSD large 4, and so overall up to BERT large being a nice 5x performance bump. And on the energy efficiency side, you see we have also a nice improvement over what was there on Xavier, so ranging up to 2.3x energy efficiency. And the key takeaway here, right? We just did our first release of ML perf on Orin. We're getting the software all in place and working to get that to productization. And so we expect to continue to see improvements, pushing up to the full capabilities of Orin. Both on DLA and GPU side, we'll see improvements, and also on the power side. So we're looking forward to continuing to push these numbers up to the max of what Xavier is capable of. So then, summing that up, where do we see Jetson? What is this going to be available to the market? Two main things, right? On the embedded kind of Jetson space, we'll have the Jetson AGX and Jetson NX based products available. Those will have up to 275 Int8 tops, up to 12 CPU cores, and up to 64 gigabytes of memory at 204 gigabytes per second. Of course, there's a range of products there. We support a TDP from 10 watts up to 60 watts, depending on the module. And you'll see within those different capabilities of max TOPS and CPU performance. And so that's the one people will be able to get their hands on and do robotics and various interesting embedded and small project space. And then we have the Drive Orin automotive platform. This is where we get high performance scaling up to 4 Orins. Here we have up to 254 Int8 TOPS. Again, up to 12 CPU cores and 204 gigabytes per second memory bandwidth. Here, in terms of TDP, we have, this runs at kind of a 50 to 60 watts air cooled, up to 100 watt liquid cooled for these platforms. Of course, these are very different temperature requirements and different characteristics, so that the power can end up being much higher. And then scaling, we can scale up to the four Orins interconnected, as we talked about. So we're excited about this. This is rolling into customers, and people are actively developing and making cars drive with this with these platforms. And so it's very exciting. And I want to just thank the team who worked on Orin. This was a huge project within NVIDIA, touching all the groups, GPU, CPU, our SoC teams, and across software to make this happen and to get this out into the market. So we're excited to see what it will do and to see it being used more and more. So thank you, guys.
All right, excellent talk. Lots of good questions coming in. Some around the difference between inference on the DLA and the GPU. So maybe I'll start there. When you're quoting the absolute TOPS numbers, are those true dense TOPS, or is that with a sparsity factor assumed?
Yeah, so that's the numbers quoted are all with sparsity.
Okay, cool. And is the type of sparsity in DLA the same type of sparsity that you have in Ampere?
Yeah, our design is intending for those to be as close as possible across the board, so that software optimized for one can run fairly seamlessly on the other, and so we try to match those capabilities in general. Makes sense.
Sabarish from Waymo asks, you have kind of a multiple ways of doing the same thing here, and you articulated during your talk that you made this in intentional decision around DLA to focus on Int8, kind of well understood networks that can map to Int8 and run very efficiently on DLA. Once you've done that, can you say anything about the relative efficiency of running on DLA compared to, let's say, running Int8 on Ampere GPU?
I actually don't have any info on that today around the efficiency difference. If I had some, I would share, but I don't know any of that off the top of my head.
Okay. And then how, like as a user of the chip, kind of what guidelines would you give people in order to, where to actually run their inference?
Right. So in general, right, DLA is intending to be a fixed function hardware block. So things that run there, I guess there's two decisions you can make. One, how big is the network? Right. We have 2 DLA instances. Those are intended to run. They run independently. So does it fit on the DLA? Do you want to run a GPU depending on your latency requirements and other things? And then what other networks do you have, and power efficiency is a big part of that. Things that can run fully on the DLA will be very efficient there. Things that need additional processing would have to go back to another engine potentially, and so that would be less efficient. So it depends on the customer. We also do benefit from some diversity there on certain customers where they want to use some of that for diversity and safety. So you have two hardware blocks. You could even run the same thing twice and get safety coverage. So.
Okay, great. Thank you. John Masters from Google asks, are you tracking ARM system ready specification with Orin? Is this something you're looking to support?
Orin is not going to be a certified ARM ARM server ready system. We are trying to align as much as possible that spec on Orin and looking towards that long term. So,
okay, great, thank you. And Shinichi Shibahara from Renaissance asks that, you've got the lockstep mechanism for the CPUs. Do you have anything similar on the DLA or GPU side?
So in general, we're using lockstep to gain ASIL D kind of coverage, right? And in compute, really lockstep is the only way to get coverage in general. And so it's pretty expensive. And so we look at trade-offs. Today, we rely to get additional coverage from kind of spatial or temporal diversity, depending on the unit, where you can run things twice or run things on different units or in parallel. And so we have a ton of safety features within the GPU and DLA, but we're not supporting kind of a dual execution mode. The cost is very high, and in general, in a lot of systems and cars, safety is covered in other higher level software means, so it's not necessary.
Okay, great. Well, I think that's it for questions. Thanks again, Michael. It was a really interesting talk, great technology, so let's thank the speaker.
And thank you guys.
Okay, so next up in this session, we have Dr. Leaf Jiang. Now, this next talk is a little bit different for hot chips in that it's actually not about a chip. So occasionally when the program committee sees a new technology that might have relevance or that might be impactful for chip designers and system architects, those sorts of submissions will be accepted in order to bring that knowledge to the chip community. And I think this next talk definitely ticks that box. So the title of the talk is NODAR 3D Vision System Enabling Mass Production of Autonomous Vehicles. The speaker is Dr. Leaf Jiang from NODAR. He's the founder and CEO of NODAR, a company that builds 3D sensors for the autonomous vehicle and robotics markets. He received his BS, MEng, and PhD, all from MIT in EECS, where he actually set the record for the world's lowest timing jitter pulsed semiconductor laser and invented a timing jitter eater device for high speed and high dynamic range A to D conversion. Prior to NODAR, Dr. Jiang was the founder of Alden Consulting Group, which is an award-winning R&D development firm. And then prior to Alden, Dr. Jiang was an associate technology officer in the director's office of MIT Lincoln Labs.
And very excited to be here today. I think the conference organizers should have thanked Ian here, I think, because in my first version of slides, we didn't really say much about what we did, and he kind of forced us to say a lot more. So in this presentation, this is probably the most comprehensive description of what we've been doing. So again, this is going to be about our 3D vision system, and we're based out of Boston, Massachusetts, and we're a venture-backed company and mostly doing software. So this is how we look at the market. We see autonomous vehicles being something that could potentially be very large, but isn't quite there yet. In the early days of sort of the DARPA Ground Challenge days, 2004 to 2007, was a time where folks were trying to figure out this problem. And one of the key takeaways getting over that hurdle of quantity one, say, was coming out with very high quality 3D information. And at the time, it was with spinning multi-channel LiDAR, which opened up a new chapter in sort of this journey. That journey continued another 15 years, another $100 billion poured into fueling that sort of innovation. And that got us from, say, quantity one to quantity 100 of these AVs. Like there's 57 cruise vehicles driving around San Francisco today. And the real question is, how do we scale this up now? Right? How do we go from 100 to 100 million a year? And for us, we believe that unlocking the high resolution 3D, that is making this a tractable problem to compute on a vehicle platform with 2 to 3 kilowatts of power, is really what's needed. And so we'll talk about that, but we believe that that hurdle is cost, reliability, range, and density, which is the things that need to be solved for the 3D perspective. So what we're building essentially is wide baseline stereo vision, but without the bar. So independent camera modules mounted wide baseline to essentially generate amazing 3D point clouds. So what we see here is a truck, 18-wheeler driving along a highway, 2.3 meter baseline system on the top looking out ahead on the road, and the corresponding point cloud on the right-hand side generated in real time. You can see all the different cars. You can see the mountains out to 2-kilometer range. So exquisite distance, which is really required for any type of highway driving. Before this, folks were not, used to seeing such long-range point clouds coming from stereo sensors, mainly because they were limited to shorter baselines. There's tons of things you can do with this. Just calling out the different objects in the scene, which is one of the most important things to do in highway driving, getting the distances to various trucks on the road, and doing so reliably in a multitude of conditions. So this is kind of a key thing that needs to happen. Taking a little step back, just what is stereo vision first off? It's basically measuring the distance to a target based on triangulation. You're measuring a parallax or a shift between two images, a left and a right sensor. So for example, a short baseline sensor here might have a very small shift for an object far away. So this sort of encoded by this yellow arrow here. But as you make the baseline wider, that shift, essentially that optical shift, is much larger, right? This green line, that shift of this car, for example, or this light is wide from left to right. And because you have that extra sensitivity, you're able to access wider ranges. And it turns out that baseline length is proportional to your range. So if you can go from 20 centimeter baseline systems of current sort of old school automotive stereo sensors to 2 meters, which is the width of a car, you can increase your ranges by factors of 10. And that gets very exciting. Why hasn't this been done before? It's because the calibration is horrendously difficult. You have to maintain the alignment of these cameras to within 1/100th of a degree, and that's virtually impossible to do mechanically with shock and vibration of an automobile. And so a few things had to come together to solve this problem today. And one of those things is being able to do the compute fast enough to solve this in software, as opposed to building a more rigid structure between the two cameras. So it's replacing mechanical structures essentially with software. So there's this decade-old online calibration problem. Folks have looked at this for a long time, being able to automatically calibrate stereo cameras in just any sort of situation. But they never really worked for automotive for a number of reasons. One being that a lot of these calibrations didn't work well in natural scenes. And second, they weren't fast enough to deal with the automotive perturbation frequencies like engine noise and road vibration. If you mount it on different parts in the car, like the side view mirrors, you get extraordinarily large vibrations. And you need to do that with exquisite accuracy. You have to do sub-pixel registration of these things to see out to 1,000+ meters. So the combination of natural scenes with high-speed corrections with high accuracy, those three things had to come together to make a real product for automotive. And so, if we look to kind of previous attempts at this is kind of a depth map showing how things could go wrong. If you have two images and they start getting uncalibrated, you get incorrect depth reported, you get things that are very dangerous, like false positives causing ABS brakes to go off. And so a lot of this is just getting the calibration right, even in high shock and vibration environments, and getting very high quality point clouds in road scenes, which are typically very hard to do with stereo because you have textureless surfaces, you have repetitive structures, and being able, over the years, including the work that we've done, we've worked very hard to make those reconstructions better. So here's an example of Ford's data set. This is an open data set. It's basically a car with a half-meter baseline stereo system driving around Detroit, and a so-called bridge. And what you'll see is, if we take the ground truth calibration values from this data set, you get this dangerous sort of situation where under the bridge it shows you that you're about to hit a wall. Basically, that's what this red means. It's right up next to you. But with our sort of calibration software, we're able to correct beyond what the ground truth measurements are. So we correct the ground truth and are able to get the correct distance to things. So just in as example, kind of scenes that we've looked at, these are a whole bunch of cases in that data set, from construction sites to tunnels to girder bridges, airports, and overcast skies and roads. And so these things need to work over a very wide variety of situations and do so reliably. So how does this work, right? And it's a pretty simple block diagram. You start with a left and right image. These cameras can be mounted, for example, on the roof, the left and right A-pillars, or they can be behind the windshields or the side view mirrors or the headlights. We've put them in a number of configurations. Physically wider is better. These images go to our online calibration block, which outputs perfectly rectified images. And those rectified images, rectified means that they're row aligned. All the features are aligned by row. And those are put into a stereo correspondence algorithm that generates a nice depth map, which can be converted to an XYZ point cloud. So for the online calibration technology, previously folks were looking at key point matching approaches. This is very common. You look at key points in the left and the right frame, you match them up, you apply an epipolar geometry constraint, and then you correct for the calibration that way. Turns out it's not accurate enough, requires hundreds to thousands of frames to average to get to some reasonable answer. And so it's neither accurate nor fast enough. And so what we've done is different. We've done a cost function based approach. The heavy details of that algorithm are in these patents up top, so you're welcome to read those. But as a sort of a quick sort of intro as to what's in those patents, because they're a little hard to read, it's essentially an optimization problem, right? So it's a 24-dimensional optimization problem. You're optimizing over the intrinsic and extrinsic camera parameters. For those that are not familiar with that, it's just basically describing all the degrees of freedom in the camera. So the extrinsic parameters are the roll, pitch, yaw, and XYZ between the two cameras. And intrinsic are related to the lens, basically. So the focal length, principal point, and lens distortion coefficients. And so if I were to brute force that and solve for what those parameters are, and assume there's 100 elements per dimension, a nanosecond per search point, it would take forever, right? The age of the universe, basically, to search that space and come up with a solution. That's why it's a hard problem. And the optimization needs to occur on every frame. So you have to do this in 100 milliseconds. So how do we do that? Well, this describes how we do it with the accuracy. It doesn't talk about the speed so much, but it's about optimizing this cost function that needs to be described effectively to get to the right answer. So input are those 22 camera parameters, and the output is basically the correct extrinsic and intrinsic parameters. The way that it works is that instead of looking at a sparse set of points, it's a dense matching approach for the error function or the cost function, whereby you look at patches of, say, H by W here, these patches that you're comparing from left to right image. And that comparison could be some of absolute differences, some of square differences. It's actually not so important, but you have some correspondence value of which you come up with a series of matches. And so you can count through the number of acceptable correspondences. That is, they pass a certain minimum value threshold and a certain uniqueness. Count those up, and that gives you the value of your cost function. And so you can optimize over those 22 parameters to get essentially the right answer there. So it does cost a bit to evaluate this function. It's very accurate, but it takes basically the operations are shown down here. It's scales with the size of the image, the size of the patch, and the number of disparities that you're searching. But provides actually on a single shot the right correct answer. There's some smartness on how you search those camera parameters in that dimensional space, but essentially this is how the algorithm works. Once the images are calibrated, it goes to stereo correspondence algorithm, and their stereo correspondence is basically deriving the depth map or matching corresponding pixels from left to right and computing that shift. And there's two sort of broad classes of how that's done. One is traditional signal processing algorithms. These are things like block matching, semi-global block matching, ELAS, and other sort of classical algorithms. And then there's a whole range of deep learning algorithms. Ton of papers since 2016, basically, on various approaches here. And so what I show here is kind of two examples. So on the left-hand side is semi-global block matching. On the right-hand side is PSMNet, which is one of the more popular accurate networks that are out there. And there's a big difference in the number of operations required per frame. There's some nice advantages of using signal processing algorithms up front. They tend to be a lot faster. That fastness comes from the fact that you're essentially doing a 1D search. You search along epipolar lines, so-called, as opposed to like a deep learning approach. It's convolutions, right? So it's always like a 2D type search. So this is fundamentally why these things take a lot longer. The other nice thing about it is that a lot of the signal processing algorithms are generalizable, and they're easier to get into, safety certified, right? So it's a little more straightforward how you do the whole ASIL certification for those types of algorithms. Okay, so where are we right now, and what can we unlock? So this is sort of an interesting slide. It says, basically, as we reduce the power of our compute, we can get into new markets. And so lower power, opens up certain markets. Right now, we're at 100 watts. For our demo, we're running currently at 5 megapixels, 5 frames per second. That's fine for mostly trucks. We're all right. As we get to consumer vehicles, it's a bit on the high side. And so in the next year or so, we want to reduce it so that we can get into sort of passenger vehicle type power levels. But reducing it even further will allow things like last mile delivery robots, and ultimately getting down to very low wattages. You can open up applications like in drones and UAVs, and smaller things that have smaller size, weight, power requirements. And so if you look at it, there is actually a physical sort of tracing here. It's roughly proportional to vehicle mass. It's like kinetic energy is 1/2 mv squared. So sort of the power produced by the platform is going to be related to its mass. Okay, so right now we're running our algorithms on general purpose, GPUs, which and they could be optimized much better. So we're consuming much more power than we would like at the time, at this time. And so to make this sort of a solved problem across all those markets before would require some sort of optimization, right? Sorry about that. And that optimization would be ideally something that could run this, calibration algorithm and stereo correspondence algorithm quickly. For example, the correspondence computation could be accelerated. Rectification with the ability to modify the lookup tables on the fly would be great. Most of the camera ISPs assume that the camera parameters are static versus time. And here we're assuming that they change on a frame-by-frame basis. So simply being able to change the ISP such that we can just update that on a per-frame basis, that is put in the intrinsics, it calculates the the remaps and can apply them immediately, that would be great in terms of things that would reduce power and make this even better. So let's see. So in summary, high resolution 3D sensing we think is key for this autonomous vehicle market. We do that through wide baseline stereo vision. And the innovations that our startup is bringing out there are online calibration of independent cameras and producing more accurate stereo correspondence algorithms. And we're likely to see that independently mounted stereo vision cameras will appear in other markets. We think that in robotics, when you look at the bill of materials, it's very unlikely that a lot of those applications can support the price points of these LiDAR systems. And so camera-based systems plus compute is perhaps a more scalable approach, especially as we get to large numbers. So with that, thank you for your attention, and happy to answer any questions.
Great. Thank you, Leif. Excellent presentation. Very interesting stuff. We've got some good questions coming in. And so first question is from Cliff Young at Google. And, you know, you did mention that the correspondence, there are some deep learning algorithms there. There seems to be perhaps a bit of a similarity with what you guys are doing and some of the newer advancements around neural radiance fields, NERF, where you're basically taking 2D images and creating a radiance field. Is there any similarity or learnings from that, or is this really kind of orthogonal technology, the deep learning components in the correspondence?
Yeah, NERF is really cool. It's so NERF is a way of generating, say, 3D information from multiple viewpoints, and it's not really meant to be as a real-time algorithm. It's typically used, from what I've seen, as a way of doing unsupervised training. So if I have a video stream and I want to have a model, I'll put that through some server, and I'll process offline what that 3D structure, ground truth, looks like. And so NERF is very powerful for that. But if I'm trying to make decisions in 100 milliseconds or less, NERF is not really I've never seen a NERF algorithm run that fast right now. But, I guess they're similar in the sense that it's multi-view kind of geometry and meshed with a network.
Right. Thank you. Another question, this one's actually from me. I think on one of the slides you had like 9.6 tops per frame for the deep learning correspondence algorithm. And you mentioned there's kind of trade-offs. Sometimes you use the DSP approach, sometimes the DL approach. If you had a lot more DL compute than you need and it was very efficient, would you just use DL all of the time, or is there still a space for the classic algorithms because maybe they're more well understood or easier to reason about?
From what I've seen as of today, there isn't a network that is both fast enough and accurate enough for a product to be deployed right now. I know there's a bunch of work, and every time you look at the leaderboards on Kitty, there's a new one that kind of pops up there. We've been compared against some OEMs have done tons of testing of us and other companies like us, and the one feedback that we got was we were the only real-time system out there, and most of these things are running post-processed. So I think we still need to keep an eye on it, and especially with compute going faster, that's great. These things haven't quite gotten there yet, as far as what we've seen. As for putting out a product sooner than later, it's really hard to beat some of these classical approaches. But we're not stuck in one camp or the other. We just want to do the best approach.
Got it. Makes sense. Thank you. Thaddeus from TenStorrent asks, is your software kind of portable across different cameras and sensors? Is it portable across different cameras and sensors? I mean, that's one of our big value propositions, is that we want to be able to play. We want to be as camera and processor agnostic. We've done a ton of cameras,
We haven't done as many processors, I would say. So in terms of cameras, we've done everything from 0.5 megapixel to 20 megapixel, global shutter, rolling shutter, Sony on semi, I mean, a whole range of cameras, even thermal cameras. So it's a pretty general algorithm. On the processor side, a lot of these things are just highly parallelizable. Obviously we've done a lot of stuff on GPUs, but it doesn't necessarily have to be. You can parallelize these things. There's several papers on using FPGAs for these type of pipelines and DSPs. And then, obviously there are vision accelerators on some of these SoCs. So, we want to build this as generically as possible and still get all the benefits of power and cost. I don't know. It's hard, but we're working on it.
Cool. Another question from Ray just came in on Slack. Ray Bear. Can the calibration obtained from the previous frame be used in the algorithm for the calibration of the current frame?
Yeah, so there is some a priori information that we know. I mean, we know that within one frame, the camera hasn't completely flipped, right? So we use that to move forward, but they are independently calculated to within some bracket. We've done a lot of off-road testing. We have a $1.7 million contract with the military. We typically don't find cameras move more than 0.1 or 0.7 degrees per frame. So that's typically a good search space. And so, in that sense, we've bound our search to what we knew before. We also have sort of two modes. We have factory calibration software. So you start off with a bigger uncertainty. So for example, if you're manufacturing headlights, which are known to within plus or minus 3 degrees, you don't want to calibrate these things off the factory floor. So that would take a little longer, but it would get the initial start, and then you would run the online calibration after that.
Right. Okay. Another question, this one from Christoph Novak. How does this change with the number of cameras? Does it get easier if you add more cameras? Does it get harder?
Yeah, so it's automotive, right? We're trying to pinch every penny. So we're trying to reduce the cameras to as few as possible. Obviously one's cheaper, but we think 2 is kind of the optimal number in terms of what we're trying to do. We do search 1,024 pixels of disparity, which allows us to bring in our minimum range very close to the bumper of the vehicle for wide baseline systems. Some people deal with that problem by adding a third camera to deal with the min-range problem, but because we're searching a big space, we could get away with 2. Adding 3 does add benefits. The usual benefit is redundancy. The second benefit is if you can mount it orthogonally, gives you some advantages in improving your correspondence algorithm. But when you look at sort of that trade of cost versus the performance benefits, we typically see people say, okay, we want as few cameras as possible. So there are benefits to going to more cameras, but I think cost pressures, especially in this market, push you to as few as possible.
Okay, great. Thank you very much. Very interesting talk. I'm sure it was very intriguing to the Hot Chips audience, so thanks a lot for that. I really appreciate it. Let's thank the speaker.
Thank you.
Okay, up next we have a talk titled NVIDIA's Grace CPU. So this is the second NVIDIA talk for this session. The speaker is Jonathon Evans from NVIDIA. Jonathon's an NVIDIA distinguished engineer and architecture lead for NVIDIA Grace. He joined NVIDIA in 2007 as a member of the GPU architecture team. And his prior work on GPU includes leading the GPU's context management and scheduling hardware team, and contributions to async compute, unified memory, multi-instance GPU, and WDDM hardware scheduling.
Hello, my name is Jonathon Evans, and I'm a distinguished engineer at NVIDIA and the lead architect for Grace. I'm here today to talk about NVIDIA's Grace server CPU. Grace is NVIDIA's first data center server CPU, and the Grace server CPU supports 72 v9.0 ARM CPU cores with support for the latest ARM ISA features, including SVE2, and full virtualization support, including nested virtualization and Secure EL2. Grace also supports ARM's RAS v1.1 specification for error reporting, ARM's GIC v4.1, which enables direct interrupt injection for virtualization and ITS support for PCI message signal interrupts, SMMU v3.1 for I/O device address translation. It is also built on TSMC's 4N process node and customized for NVIDIA. The Grace CPU has been designed from the ground up to be the world's first superchip. The Grace CPU is built to pair with NVIDIA's Hopper GPU to create the Grace Hopper superchip, or with another Grace to create the Grace superchip. The Grace Hopper and Grace superchips are enabled by NVIDIA's NVLink C2C high-speed interconnect. NVLink C2C is the backbone by which Grace and Hopper communicate. The high-speed interconnect eliminates the typical cross-socket bottlenecks, and this interconnect can provide up to 900 gigabytes per second of raw bidirectional bandwidth. This is 7 times the bandwidth that can be delivered by this typical by16 PCIe Gen 5 link. And it also does this at both lower power and lower latency than PCIe, and is up to 5 times more power efficient while delivering that 7 times additional bandwidth. NVLink C2C is also a coherent interconnect, which enables coherency whether you're programming a standard coherent CPU platform on the Grace superchip or a heterogeneous programming model with the Grace Hopper superchip. So the Grace superchip is designed to offer a standards-compliant platform for all software developers. These specs are included as part of ARM's System Ready initiative to bring standardization to the ARM ecosystem. Grace targets ARM system standards to offer off-the-shelf operating system and software compatibility. Grace has been designed to follow the ARM server-based system architecture, or SBSA, to enable standards-compliant hardware and software interfaces. Grace will also support the ARM server-based boot requirements, or SBBR, to enable standard boot flows on the system. Grace also supports ARM's memory partitioning and monitoring feature, or MPAM, for cache and bandwidth partitioning, along with monitoring of bandwidth. And Grace includes ARM performance monitoring units, also known as PMUs, for both CPU and uncore performance monitoring. And this is enabling standard tools such as Linux Perf to be used for performance investigations on the architecture and the chip. The Grace Hopper superchip combines a Grace CPU with a Hopper GPU. This superchip expands upon the CUDA unified programming model first introduced in CUDA 8.0 and allows the GPU to share the address space and even page tables with the CUDA application. The Hopper GPU is also able to access pageable memory allocations within the system. The Grace Hopper superchip allows you to use system allocators for allocating GPU memory, and yes, you can even exchange pointers for plain old malloc and mmapped memory with the GPU. The C2C interconnect also enables native atomic support between the Grace and Hopper chips, which unlocks the full potential for C++ atomics, which were first introduced in CUDA 10.2. NVLink C2C also enables the Grace Hopper superchip for scale-out design and deployments. With Grace Hopper, NVIDIA is introducing extended GPU memory. This technology allows any Hopper GPU connected over the larger NVLink network to access the LPDDR5X memory connected to the Grace chip in the Grace Hopper superchip. The GPU to GPU NVLink and NVLink C2C bidirectional bandwidths are matched up in a Grace Hopper superchip. And when the superchips are connected over NVLink, this gives you native NVLink speed access to Grace's memory for all the Hoppers in the system. With EGM, you have unprecedented scale out for GPU memory accesses across NVLink at native NVLink speeds. NVIDIA Grace introduces NVIDIA's Scalable Coherency Fabric, also known as SCF. SCF is an NVIDIA-designed mesh fabric and distributed cache ready to scale to the needs of the data center. Grace's SCF mesh has a bisection bandwidth of over 3.2 terabytes per second to keep traffic flowing between the NVLink C2C, the CPUs, memory, and the various system IOs. A single Grace supports 72 cores and 117 megabytes of cache, but the SCF is designed to scale beyond that. When configured as a Grace superchip, there are 144 cores in the system and 234 megabytes of distributed L3 cache across the two chips. The CPU cores and the SCF cache partitions, also known as SCCs, are distributed throughout the mesh. The cache switch nodes, or CSNs, route data through the fabric and act as the interface between the cores, caches, and the rest of the chip, and enable the incredibly high bandwidth throughput you see in Grace. The Grace Hopper superchip also supports multi-socket coherency, and up to 4 chips may be used to create a 4 superchip coherent node. NVIDIA Grace also supports ARM's memory partitioning and monitoring feature known as MPAM. MPAM is the ARM standard for partitioning system cache and memory resources. MPAM works by assigning partition IDs, also known as part IDs, to requesters within the system, and resources such as cache capacity, memory bandwidth can be partitioned or monitored based on the part ID that's been assigned. The SCF cache supports both partitioning of a cache capacity as well as memory bandwidth using this MPAM feature. The SCF also supports the use of performance monitor groups, or PMGs, for monitoring resources by part ID. Next up is the memory interface. The NVIDIA Grace SoC supports 32 channels of LPDDR5X memory with up to 512 gigabytes of memory and up to 546 gigabytes per second of aggregated speed of light memory bandwidth. But you're probably wondering, why does Grace support LPDDR5X memory and not the typical DDR memory? Remember that NVIDIA Grace is designed to be part of a superchip. Well, the superchip focus design means that Grace is always paired with either a Hopper GPU or another Grace CPU. So why would we pick LPDDR5X? Well, we had different options we could consider when choosing memory technology for Grace, all with different trade-offs. We could have chosen HBM2E, as that provides a massive amount of memory bandwidth at a low power, but at a very high cost. And the capacity of HBM is very, very limited. 4 sites of HBM only gets you around 64 gigabytes of memory, which is not enough for our typical compute workloads. We could have chosen a more traditional 8-channel DDR5 design. DDR5 certainly provides a lot more capacity, over a terabyte, but does so with a much lower bandwidth, but at a better cost per gigabyte than HBM. What we decided to use was LPDDR5X, which is a technology we have experience with on our other SoCs, such as Orin. LPDDR5X affords us up to 546 gigabytes per second of bandwidth and capacity, but does so at a similar power per gigabyte as HBM2E, but at the same cost of DDR5. Additionally, the lower power of DDR5X lets us devote significantly more compute power towards compute resources, such as the CPU cores or GPU streaming multiprocessors, as opposed to using that power to drive the memory interface. And if you also remember, NVLink C2C is capable of over 900 gigabytes per second of bandwidth. And as such, we have an opportunity to make use of that memory bandwidth within our superchips. While HBM does have more memory bandwidth than LPDDR5X, we feel that the capacity trade-off of LPDDR makes LPDDR5X the right choice as compared to the other options. So how much memory do you actually need? And why does LPDDR provide the right capacity choices? So let's take a look at one common task someone might run on a Grace Hopper superchip: natural language processing. GPT-3 is a language prediction model used for predicting text. GPT-3 is a huge model at 175 billion parameters and takes up to 175 gigabytes of memory if you're using floating point 8 as a representation. That's certainly not enough to fit into a single GPU's memory, but this can fit into Grace's memory. With the NVLink C2C, the GPU has high-speed access to that memory as well, allowing you to run GPT-3 inferencing on a single node. Also, when it comes to training, GPT-3 is also a beast, taking over 2.5 terabytes of memory. While we can't fit everything into Grace's memory, we have the extended GPU memory to come to the rescue. With Grace Hopper Superchip and extended GPU memory, you actually can use 4 times fewer GPUs to fit everything into the memory of your system. And so with NVLink scale-out, you have over 100 terabytes of fast memory that can be available for Grace Hopper Superchips to use for training in your machine learning workloads. Grace supports a complement of high-speed I/O to enable data center use cases. The Grace SoC supports up to 68 lanes of PCIe Gen 5 and up to 4 Gen 5 by 16 links for I/O connectivity. Each of the Gen 5 by 16s support up to 128 gigabytes per second of bidirectional bandwidth, and each by 16 link can be bifurcated into 2 by 8s for additional connectivity. We also support 12 lanes of coherent NVLink shared with 2 of the PCI by 16s, which can be used to connect multiple Grace Hopper Superchips. We've also have our NVLink CDC, which I talked about earlier, which enables us to build both the Grace and the Grace Hopper Superchips. But Grace is not just about the Grace Hopper Superchip and accelerator-based workloads, but the Grace Superchip itself is purpose-built for supercomputing and HPC. There's the 144 ARM v9.0 cores supporting SVE2 are targeted at leading single-threaded performance. The Superchip has up to 1 terabytes per second of memory bandwidth and utilizes the NVLink C2C to provide 3 times your typical inter-chip bandwidth between the chips. The LPDDR5 memory also provides an energy-efficient design with a total 500-watt TDP for the 2 Grace chips and the LPDDR memory and the entire module. This allows you to have more power for your compute. Now for a few benchmarks. A single Grace CPU SoC has an estimated spec int rate 2K17 score of 370. And the Grace Superchip has an estimated spec int rate 2K17 score of 750. And these are currently pre-silicon estimated results and are based on using the GCC compiler and subject to change. Memory bandwidth is incredibly important to us, and Grace is no slouch here either. These benchmarks are also pre-silicon simulation results for single Grace SoC. As you can see, we achieve over 92% of the theoretical speed of light memory perf when running the stream benchmarks. And many systems only reach around 80% of the theoretical peak under load. Well, what about across the NVLink C2C, you might also ask? Our GPU to CPU memory benchmarks show that the NVLink C2C is not going to be a limit for GPU performance. The Hopper GPU can achieve a full 506 gigabytes per second of traffic to Grace's memory, fully saturating the LPDDR memory system. And this is at over 92% of the theoretical achievable bandwidth across the interface. In summary, Grace is NVIDIA's first server SoC, supporting 72 ARM v9.0 cores, NVLink C2C to enable NVLink to build the first superchips, LPDDR5X, which gives you low power, high bandwidth memory, and extended GPU memory to enable the multi-node scale out. And finally, but not least, a huge thanks to the entire Grace SoC team. Many people have contributed to making Grace reality, and none of this would have been possible without all of your teamwork and contributions to the project. Thank you, everybody. And I may be excited to answer questions. So please send me your questions and we'll have a Q&A. Thanks.
All right. Thanks, Jonathan. Lots of questions coming in. Before we dive into the questions, I'll just reiterate something I put in Slack, in that Jonathan's unable to speak to the specifics of the CPU core inside of Grace at this time. So please don't be upset if I ignore your question about the CPU core. All right, so let's just dive right in. Xiaoyu Ma from Google has a question around the the 900 gigabyte per second interconnect. Obviously, this is a very impressive amount of bandwidth. Can you share a little bit about the scenarios in which you actually use all of that bandwidth, or when you're potentially bandwidth limited?
Hello? Okay, thank you. Yeah, so as I discussed in my talk, various workloads where you would typically run out of memory from the GPU. In some cases today over NVLink, you might do scaling by connecting multiple GPUs just to make use of their memory. Basically, you have access to that at what would be NVLink, scale out speeds, but to your local system. So, anytime you have a problem that doesn't fit in GPU memory, you're able to, get that performance you need.
Okay, thanks. And regarding the CDC NVLink, does that actually require like a silicon interposer inside the package?
No, NVLink CDC does not use a silicon interposer. It's through PCB technology.
Can you say anything about like the ECC scheme for the LPDDR?
So our ECC scheme, we've made changes to it since our other Tegra chips, but ECC there has been optimized for the data center. So that's about all I can say.
Okay. Thanks. So you spoke a bit about the shared page tables and atomics. Are there any kind of issues or challenges you faced in terms of making that work? Like, any performance bottlenecks or things you had to work around shared page tables and atomics between CPU and GPU?
Yeah, so making that work well requires having a really high speed performance ability to do translation. So you don't want to be limited by your translation performance. So that's something we had to pay careful attention to based on the workloads and the fact that we have a very high speed interconnect. And the GPU tends to chew through TLBs very quickly. So.
Nathan Brookwood asks, what's the latency penalty when a Grace CPU has to access the memory attached to another chip?
Yeah, so we're not giving any individual information about like core performance. So at the moment, I'll have to decline answering that, but thank you.
Okay. Nathan also asks, and this question came up earlier, can you say anything about how TSMC4N differs from maybe a standard TSMC process?
Yeah, so our process team is working with TSMC to always customize the process to fit our particular chips. But I don't have any details I can give about exactly what those customizations look like.
Okay, thanks. Hiroyuki Ishii from Fujitsu asks if Grace's on-chip interconnect uses ARM Neoverse IP, or is this a proprietary interconnect?
So the interconnect, the SCF I discussed, is NVIDIA proprietary interconnect. So it's our internal fabric team has designed it.
So question from John Masters at Google. What was your greatest takeaway in making Grace so awesomely compliant with the system ready specs?
I think that the biggest takeaway is that you get the advantage of being able to just boot off the shelf OSs. It reduces the complexity to support the board and the system. And so being able to boot up to standard OS just eases the development process.
Question from Matthew earlier from Ampere. We touched about this a little bit, but can you comment just in general around the reliability of LPDDR5 in the scenarios you guys are looking at?
Yeah, so we've looked at the needs for the data center. So our LPDDR technology, we expect to meet the data center reliability needs. So.
Okay, great, thank you. Ravi Chandran asks, can you say anything about frequency and TDP?
TDP, I think I mentioned, the Grace Superchip has a 500 watt TDP. That's both chips and the memory.
Great. Okay, I think I got through most of the questions. Another one just came in here. Asmita Najor from Intel. During the March GDC keynote, an example Grace Hopper system was shared, one with 2 Grace and 8 Hopper. In that system, are they basically over PCIe or NVLink?
Eight of those would be over PCIe.
So Sissy1 from Grok and Stanford asks if you could kind of discuss a bit about any power saving aspects of LPDDR in terms of like shutdown or sleep.
No, I don't have anything to really add there. Yeah.
Thanks. Okay, great. I think I've gone through most of the questions. Feel free to pull them in, and maybe we'll get a chance for Jonathon to answer them. Thanks a lot, Jonathon, for the talk. Super exciting, great technology. Really great. Thank you.